In this lesson, we will study the concept of the incircle. So, by definition, a circle is said to be inscribed in a triangle if its center is interior to the triangle and all three sides of the triangle um, tangent to the circle. So, you will see on the screen a red circle which is inscribed inside a blue triangle, and as you can see, the radii of our red circle are all tangent to the three sides of the triangle. So one of the important thing that we'll see in this video is that every triangle actually has a unique circle which is inscribed inside that triangle. The center I of the inner circle of a given triangle is called the incenter. So in this case here, I is the incenter, and the length of the radius of the incircle R is the in radius of the triangle. Okay, so to summarize, given any triangle, say A, B, C, it has a unique circle which we call the inscribed circle of the triangle. The center is called the incenter of the triangle, and the length of the radius of the inscribed circle or the incircle is called the in radius of the triangle. So here's a little animation which shows you how to construct the incircle and the incenter of a given. Alright, so our first result in this lesson is a lemma, and the lemma is stated as follows. The bisector of an angle ABC is the locus of point P in the interior of the angle that are equidistant from the sides of the angle. Okay, so suppose as shown in this picture that px is equal to py. It is not hard to see that the triangle PXB is congruent to the triangle PYB. So I'm looking at the triangle PXB, this triangle here, and then the triangle PYB, right? So it's a simple exercise to verify that these two triangles are congruent. So as such, we can then say that the angle XBP, this angle here, is congruent or equal, let's say in measure, to the angle YBP, which is this angle there. So consequently, line BP is the bisector of angle ABC, and thus we can then conclude that P lies in fact on the angle bisector of angle ABC. Now for the converse, suppose let us suppose that BP in fact bisect angle ABC. It is also again easy. It is an easy exercise to verify that triangle PXB is in fact congruent to triangle PYB, and this is actually a consequence of SAA, and as a result PX is indeed equal to PY as desired. So remember that one of the main aim of this lesson is to prove that any arbitrary triangle has a unique incircle. Okay, so in our quest to establish these results, this lemma is in fact of central importance. And not this lemma, this theorem is of central importance. This theorem states that the three-angle bisector of a triangle are concurrent at a point I. In other words, if you give me a triangle, and if I look at the three angles which are interior to my triangle, and then I bisect each one of them, right? So I get three lines in fact passing through the vertices of the triangle. Then all three of these lines are actually going to meet at a unique point. So this is something very special here, because generically it's not true that three arbitrary lines are going to be concurrent. So the fact that the three-angle bisector of a triangle are concurrent at a point I is a very special property, which is not, of course, apparent. So we'll try to establish that. Now, the point also is that this point I here is in fact equidistant from the sides of the triangle, and if we denote the R by if we let R be the distance between this point I, which is at the intersection of the three angle bisector of our triangle, then the circle which is center at I and of radius R is actually the unique circle, is the incenter of our triangle. So this is what we are trying to prove. So having explained this theorem, let's get started with the proof. So let ABC be a triangle which is shown on your screen. Now I will look at the first angle at B, and I'll bisect that angle, and I'll look at the angle at C, and I'll bisect that angle. So I get two lines, and since those two lines are not parallel, in fact you should pause the video and try to justify to yourself why the two bisectors of angle B and C cannot be parallel. But in any case, accepting the fact that those two lines aren't parallel, then they must meet at a point I. Okay, and now let's proceed as follows. What we do next is so next observe that from our previous result, so by the previous lemma, we know that IU is equal to IW. So let me remind you why this must be the case. The previous lemma tells us that The bisector of angle IBC is the locus of points in the interior angle that are equidistant from the side of the triangle. Okay, so the fact that IB is a bisector of angle B allows us to say, by appealing to the previous lemma, that IU must be equal to IW. Next, so this is the case since I lies on the bisector of angle B. Now, similarly, since I lies on the bisector of angle C, then we can see that IU must be equal to IV. So consequently, we have that IV is equal to IU, and okay, no, that I mean to say that IV must be equal to IW, taking these two into account. And by the previous lemma, you can almost guess what's about to happen here if you are paying attention. By the previous lemma, I lies on the bisector of angle A. Next, let's put R to be equal to IU, which is now of course IV, which is also IW, and the circle centered at I with radius with radius R is the incircle. In fact, is the unique incircle of the triangle ABC. And this gives us exactly what we want. In previous lessons, we have seen and we have proved two important laws known as the law of cosines and the law of sines, respectively, are shown on the screen. In this lesson, we will use our new concept that we have introduced to actually derive another law, which is called the law of tangents. Alright, so the law of tangents can be stated as follows. In a triangle ABC, let the quantities A, B, C, and S have their usual meanings. Remember that S is a semi-perimeter. So in other words, it's A plus B plus C over 2. Then tangents of angle C over 2 is equal to the square root of the product S minus A, S minus B over the product S minus S times S minus C. Alright, so let us prove these results. Okay, now first let us consider the illustration on the right hand side of your screen, where you can see that UI, IV, and IW are the in radius of our incircle. Now, since IC bisect angle C, then considering the triangle IUC, it is clear that tangent of C over 2 must be equal to the opposite side, which is UI, over the adjacent sides, which is equal to UC. Now, moreover, we'll put little x to be equal to AV, which is of course going to be okay, so which we also set to be equal to AW, and let y be BU, which is equal to BW, and let z be CU, which is CV. Then you can see that UC is going to be the perimeter, right, which is 2s, since s is half of the perimeter, minus 2y plus z plus 2x. So we take the perimeter, we remove 2y, so we remove this side, we remove this side out of the perimeter, and we remove 2x, and we're left with UC, which is of course z. Now expanding this out gives s plus s minus 2y minus z minus 2x, which is equal to s plus x is s is of course x plus y plus z, because it's a half of a perimeter, minus 2y minus z minus 2x, and after cleaning things up we get s plus negative x minus y, right? This and this will give us negative x, this and this is going to give us negative y, and these two cancel each other out, and then we can factor negative out, and this shows that UC is actually s minus c, because x plus y, right, you can see that x plus y is the measurement of AB, which is equal to c, since x plus y is equal to AB, which actually is set to measure c. Okay, so let's actually consider this much cleaner picture, and so to proceed, I'll make the observation that the area of ABC is precisely the area of IBC, which is the yellow triangle, plus the area of IAC, the green one, plus the area of IAB, which is the blue one. Now let's look at the yellow triangle here. Now its height is r, right, the in radius of our circle, and its base is measures a. So the area of IBC will be half RA. For the green one, we'll have half r. Again, the radius is still r, and its base, the corresponding base, is b. And for the blue one, the height is r and its base is c. So factoring 1/2 r out gives us this formula. Now since the area of a triangle ABC is the square root of s times s minus a times s minus b times s minus c, we take the square root of this, and notice that I can rewrite this here as r times a plus b plus c over 2, and that's half of a perimeter, so that's actually RS. So this will be equal to RS. So now we have that square root of S times S minus A times S minus B times S minus C is equal to R times S. Now we'll consider this equation here, and then we'll solve for R. Solving for R gives square root of S times S minus A times S minus B times S minus C over S. And okay, so this is going to be in fact square root of S times square root of S minus A times S minus B times S minus C over S, which is square root of S minus A times S minus B times S minus C over square root of S, and we can put everything under one radical, so we get this S minus C over S. Okay, now so the point here that we're making is that tangent of C over 2, right? So looking at this angle here, I mean this triangle, let me highlight this triangle. So we are looking at this triangle here. We all agree that because IC bisects C, this is going to be C over 2. So the tangent of C over 2 is going to be opposite, which is IU over UC, right? All right, now IU is so IU is R, right, which is square root of S minus A times S minus B times S minus C over S, and UC, as we saw, is S minus C. So this will give us we can write this as square root of S minus A times S minus B over S times square root of S minus C over S minus C. Now looking at this, right, this is so the denominator, we can sort of simplify this and we get square root of S minus C here. And then this will give us precisely that we get square roots of S minus A times S minus B over S time 1 over square root of S minus C, and then we can put everything under the same radical. Gives us S minus A, S minus B over S times S minus C. And this gives us the desired result. We have in fact proved that tangent of C over 2 is going to be the following. If we let S be the semi-perimeter, which is half of A plus B plus C, is going to be square root of the quantity shown on the screen. In order to look at our next results, we will first study this lemma, this intermediate result, which is stated as follows. If you extend the bisector of one of the angles of a triangle to meet the circumcircle at some point P, remember the circumcircle is the circle containing on which the triangle is inscribed. So we extend, let's say, the bisector of angle A to meet the circumcircle at some point P as shown on the screen. Then the distance from P to C to each of the other two vertices of the triangle is equal to the distance IP, where I is the center of the given triangle. So we would like to show here that, so our aim, we aim to show that IP is equal to CP. So to this end, so to prove that IP is equal to CP, it is enough. So to this end, it will suffice to apply Pond's Asinorum theorem to the triangle IPC. Okay, so now let's look at angle BAP. This angle here. Okay, so we consider the angle BAP and we consider the angle BCP. So you can guess what I'm about to see. Since angle BAP and angle BCP subtend the same arc. For us here is this arc here, BP. They also obtain the arc BP. Then we of course they must be equal to each other. The measure, I mean, they're equal to each other in measure. That's what I mean. They're not the same angle, they're just equal to each other in measure. Okay, all right. So so in fact, we can say much more than that. We can say that the angle BAP is equal to angle BCP and is equal to half of the measurements of arc BP. All right. So next, since IC bisect angle C, then we can say that angle ICB is half of the measurement of angle C, and angle ICP is then going to be equal to 1/2, right, of angle A plus angle C. Okay, so the point here is if we look at this angle here, ICB, right, that's 1/2 of angle C. Now the angle BCP is 1/2 of angle A, so the sum, which is angle ICP, is going to be 1/2 of the sum of the angle of A and B. Next, angle P is equal to angle B, since of course they subtend the same arc. Angle P here and angle B subtend this arc here. So they're the same. And angle ICP plus angle CIP, so ICP, which is this here, plus CIP, which is in that, is going to be equal to 180 degree minus the angle of P, and this is obtained. This observation is coming from by looking at the triangle ICP. Yeah, so because angle P and angle ICP and angle CIP are interior angles to the triangle ICP. Okay, and then that's equal to 180 degree minus angle B, which is angle A plus angle C, and this is obtained by looking at, so C, the triangle ABC. Okay, so in summary, thus we have that angle CIP is equal to angle A plus angle C minus 1/2 of angle A plus angle C. Right? So angle CIP, so this is CIP, is going to be equal to, so if we take this equation here, right, and then we solve this for angle CIP, we get that angle CIP is angle A plus angle C minus angle ICP, but angle ICP is 1/2 of angle A plus angle C, and this is precisely 1/2. We're taking something and we're subtracting its half, so we are left with a half of the original quantity. This is precisely also equal to angle PCI. So by Pons Asinorum, we can then conclude that IP is equal to PC, and this is the desired result. So recall the power of the point theorem. So according to this result, if you have a circle and given a point in a circle passing suppose you have two lines passing through our circle. In fact, you have two chords, and then these two chords are determined by the pair BC and AP respectively. Then the product AP times DP is an invariant for the circle, meaning that the value of AP times DP is not a function of the choice of the chords. In other words, AP times DP is going to be equal to BP times PC, and you can choose your points to be inside the circle, you can choose your points to be outside of the circle, and the outcome is going to be the same. Okay, so that being said, we will need these results for our results for the subsequent theorem. In order to prove our next result, we also need to review the extended law of sines, which states the following. Given a triangle ABC with circumradius R, big R, and let a, little b, and little c be the length of the sides opposite to vertices big A, big B, and big C respectively, then the ratio A sine of big A, little b, sine of big B, little c, sine of big C is actually equal to the length of the diameter of the circumcircle of the triangle. All right, so this is an ingredient that we'll need for our next result. All right, so our next result, known as Euler's theorem. Euler has many theorems, so I guess this is another one of his important results. Says that if we let D be OI, the distance from the circumcenter to the incenter of an arbitrary circle, of an arbitrary triangle, I mean, then d square, so the sum of the square of the distance between the center of the circumcircle and the center of the incircle is equal to r time big R minus 2 little r, where big R is the circumradius and little r is the in radius. All right, so let's get started on the proof of this result. So first, notice that if we let xi be big R minus little d, right? So all of these, so notice that this is the case because big R is equal to OX, and since xi is in fact OX minus OI, then we get OX is going to be R minus little d. Okay, and then yi is big R plus d. Notice again that here yi is io, right, plus oy, but io is again d and oy is big R. Okay, now by the power of the points theorem, we have that xi, the product xi, and that of yi will be equal to that of ai time ip, which is going to be equal to r square minus d square, and by the previous lemma, IP is equal to PC, right? Okay, we've seen earlier that IP is equal to PC. Next, since angle PAC here is half of angle A, right? Because AI bisect angle BAC, we obtain that PC over sine of A over 2 is equal to 2R, and this is by the extended law of sines. Okay, so now we'll have that r square minus d square is equal to AI times IP, correct? Which is AI time PC, because IP is PC, which is AI time, so solving this for PC gives 2R sine of A over 2. I will call this here star. Next, we consider the triangle AIF. This triangle here, AIF. And since IF is little r, we know that sine of A over 2 is going to be equal to R over AI, right? Your hypotenuse. And as such, AI times sine of angle A over 2 is equal to little r, and by, okay, so just say by star, we know that r squared minus d squared, AI is big R, and okay, so if we look at star, then we know that AI times sine of A over 2 is little r, so we'll have 2R big R little r. Now we'll solve this equation for this, for d squared minus 2RR, and then we can factor one big R out, and we get R minus 2 little r, and this is the desired result.